Hello friends, I am Somnath Bhomik from Department of Material Science and Engineering, IIT Kanpur. Welcome to the first lecture of the course on electronic properties of the materials. In this lecture, I shall briefly explain the scope of the course. Let me start by showing a transistor, which is one of the basic building blocks of modern electronics. In particular, I am going to talk about metal insulator semiconductor field effect transistor. In the left hand side, actual devices are shown. The matchstick is shown as a scale to give you some idea about the size of the actual devices. In the right hand side, main components of the device are shown schematically. Current flows from drain to source via a region known as the channel region. And the current can be controlled by applying a gate voltage. No different class of materials used in the device. The channel region is made of semiconductor. There are 3 metallic contacts in source, drain, and gate. This is shown by the green color. The gate electrode is separated from the body or channel region by an insulating layer. Right? This is shown in the red color. Thus, we need 3 different classes of materials to make the device: metal, semiconductor, and insulator. Let us explore the periodic table in search of metals, semiconductors, and insulators. When individual atoms come together to form a solid, their properties depend on the type of bonding holding the constituent atoms together. Looking at the periodic table, most of the elements form a solid via metallic bonding, and some of them forms a solid via covalent bonding. For example, if you look at this region, right, the yellow region, all of them, they are forming a solid via metallic bonding. And if you see the small region shown in blue, they are forming a solid via covalent bonding. Covalent bonding takes place via hybridization and overlap of atomic orbitals. For example, in silicon, sp3 orbitals form the covalent bonds with a bond angle of 109.47 degrees. Metallic bonding takes place via valence electrons, which becomes free from the core and forms a sea of free electrons. The ionic cores are submerged in the sea of the free electrons. Ionic cores are much heavier than the free electrons and remain fixed at certain points known as the lattice points. For example, if you look at this figure, this dark region, these you can consider as cores. And then outside the core electrons, you have this diffuse region, right? And these are the valence electrons. And you see that these ionic cores, right? They are at some points known as the lattice point, and they are very heavy and they don't move. And the valence electrons, they become almost free and they will move around in the solid. And that's how the metallic bonds are formed. Ionic bonds form among positively and negatively charged ions arranged in a lattice point. Obviously, ions of opposite charge are held together by Coulomb interaction. For example, if you take sodium chloride, then this black points, these are the chlorine atoms, and the white points, these are the sodium atoms, and that's how they are arranged in a lattice, and they are held together by Coulomb interaction. In this slide, I show the classification of elements in terms of their property. The elements forming metallic bond are metals. There are further subclasses For example, we have alkali metals, we have alkaline earth metals, we have transition metals, and you see these gray boxes, these are like classified as other metals. Elements forming covalent bonds like boron, carbon, silicon, germanium, etc. These are known as metalloids. You need two different elements to form ionic bond. When an element combines with oxygen, nitrogen, chlorine, iodine, etc., to form compounds like oxides, nitrides, chlorides, iodides, etc., such compounds are generally classified as nonmetals. Generally, these are formed by ionic bonding. Thus, based on bonding, we have broadly divided the materials in three different categories: metals, nonmetals, and metalloids. Metals have shining appearance. They are good conductor of heat and electricity, and they are ductile. That means they can be deformed without breaking them. On the other hand, non-metals are dull in appearance, and they are very poor conductors of heat and electricity, and they are usually brittle. That means they break easily. Now, metalloids, their properties lie in between the properties of metals and non-metals. So metalloids are conductor of heat and electricity, but they are not usually as good as metals. And these metalloids, they are generally very good semiconductors. Thus, we know that the properties of metals, nonmetals, and metalloids differ significantly because of bonding. Since this course is on electronic properties of materials, I show you a comparison of electrical conductivity of different elements present in the periodic table. So if you look at the metals, mainly this reddish region, then you see that the conductivity is very high, that is of the order of 10 power 6. Whereas if you look at the metalloid like silicon and germanium, the value is only 10. That means there is a difference of 6 orders of magnitude. In this course, we will try to understand why such a huge difference exists between metals and metalloids. Not only the order of magnitude of electrical conductivity in a metal and semiconductor differ, but also the way its resistivity changes as a function of temperature, that also differs completely. For example, if you take copper and increase its temperature, then its resistivity is going to increase. On the other hand, if you take silicon and increase its temperature, then in that case, the resistivity decreases as a function of temperature. Then there is a third class of materials known as superconductors, for example, lead. In such materials, below certain temperature, the resistivity suddenly drops to 0. This is just for your information, and we are not going to discuss about superconductivity in this course. Let me briefly explain the aim of the course. So far, we have seen that metals have low resistivity than compared to semiconductors, and the difference is 6 orders of magnitude approximately. Moreover, the resistivity increases in metal with increasing temperature, whereas in semiconductors, resistivity decreases when temperature is increased. So we will try to understand why do we observe such things. In order to understand that, we will start with free and independent electron gas model. And such a model ignores the electron ion and electron-electron Coulomb interaction. And such model can be explained at 2 different levels. First is classical free electron gas model, and the second is quantum free electron gas model. And we will see that the free electron gas model, particularly the quantum free electron gas model, can explain some of the properties of the metals very well. And then we have to go beyond free electron gas model, and we have to include electron ion interaction, where the positive ions arranged in a lattice provides the periodic potential for the valence electrons. And once we do that, then we will see that we can get very good explanation for the properties of semiconductors and insulators. Let me briefly mention the fundamental concepts and technical skills to be developed during the course. So we will start with classical free electron gas model. For classical free electron gas model, we need to know a little bit of classical mechanics and electrodynamics. Then we do quantum free electron gas model, and for that we need to know the basics of quantum mechanics. For example, Schrodinger equation, wave function, probability density, expectation value, uncertainty principle, wave particle duality, etc. Then we will learn the analytical solution for different potentials like free particle, particle in a box, harmonic potential, tunneling, etc. After that, we will also learn how to solve Schrodinger equation numerically for different potentials. Then we do electron in a lattice or electron in a periodic potential. For that, we need to learn a little bit about the basics of real lattice, reciprocal lattice, and diffraction. So after we are done with the fundamental part, we will learn a little bit about the application. And in application part, we will learn about traditional semiconductors and ionic conductors like silicon, sodium chloride, etc. And then we will learn about state of the art, for example, 2D materials like graphene. Throughout the course, Python programming will be used for numerical solution and visualization.